I will be talking about the nonlinear attenuation of acoustic waves in bubbly mediums. Bubbles have many applications, and they are the building block of many applications, from material science to medical ultrasound. For example, in medical ultrasound, they're used as imaging techniques to visualize blood vessels, and also in therapeutic ultrasound as a means for drug delivery. The nonlinear oscillations of the bubbles in imaging can be used to suppress the signal from the tissue. Here we see an image of a 300 millimeter blood vessel at 20 megahertz while it's perfused with the microbubbles, and by just looking at the subharmonic signal from the microbubbles, we are able to suppress the signal of the tissue and just visualize the blood vessels. Also, the oscillations of these bubbles near the cells create shear stress on the cell wall, and it increases the permeability of the cell to the previously impermeable macromolecules, and they can go into the blood and they can go into the cells much more easily. However, when we administer these bubbles into the medium, many of the acoustic parameters of the medium changes. The presence of the bubbles increases the attenuation, and it changes the speed of sound. For example, in high-intensity focused ultrasound heating, which is another therapeutic applications of bubbles, or in drug delivery, we use focus beams to a target, and the presence of the bubbles prefocally will increase the attenuation, and we're not able to deliver enough energy to the bubbles at the focal point. Either these bubbles should be destroyed prefocally by a high pressure wave, or we should know the dynamical behavior of the attenuation of the medium in the presence of the bubbles and optimize the frequency and pressure to increase the pressure waves that are reaching to the target. However, current studies only use linear models to estimate the attenuation of the medium in the presence of the bubbles, and nonlinear dynamics of the bubbles are not fully understood. First, we need to understand the nonlinear dynamics of the bubbles, and then we should have a model which is valid in the regime of nonlinear oscillations. The current models are only valid for very small microbubble oscillations, and they are only valid in linear regimes of oscillations. So the goals of this study is to develop a model to incorporate the nonlinear bubble behavior in attenuation calculation, and classify the nonlinear bubble dynamics, and through that classify the attenuation regimes that we may encounter in applications. The Calfish model has been developed and been referenced a lot for the propagation of the waves in a bubbly medium, and it is simply the wave equation where there is a term related to the changes of the density of the liquid, which is related to beta, which is the void fraction that accounts for the presence of the bubbles. And this void fraction oscillates as it is the volume of the bubbles in the medium, and then the radial oscillations of the bubbles are nonlinear. Void fraction oscillates nonlinearly. The linear model, which is developed and has been used for many years, is developed by Commander and Prosperity, and this model is only valid for very low acoustic pressures and for very small bubble oscillation amplitudes. Commander and Prosperity linearized the Rayleigh-Placid equation and at very low acoustic powers, and fit it into the Calfish model, and they were able to find the wave number squared in this form. So the wave number squared in the linear model depends on the number of the bubbles in the medium, the initial radius of the bubbles, the resonance angular frequency, and the angular frequency of the transmitted wave, and also the total linear damping. And the damping that's used here is also linear. Recently, another model was developed to account for the nonlinear attenuation of the waves in a bubbly medium by Louisnard, and he found the imaginary part of the wave number squared using in a nonlinear way, but it still uses a linear model for calculating the real part. So in his model, the time average imaginary part of wave number squared depends on the time average nonlinear total damping of the bubbles, which is the thermal damping, the viscous liquid damping, radiation damping, and the damping due to the viscosity of the shell. And it depends also on the pressure of the transmitted wave. So each of these dampings depend on the pressure, and also there is a dependence on the pressure. However, the Louisnard model cannot estimate the pressure dependence of the real part of the wave number squared, and thus the calculation of the attenuation will suffer a lot of inaccuracies, especially in the regimes of resonance and pressure dependent resonance of the bubble. We use the Calfish model, and we wrote it into two simple forms for the pressure and the complex conjugate of the pressure of the wave field, and with very simple mathematical derivations, we were able to find the real part of the real part of the wave number squared and the imaginary part of the wave number squared. So as we see, the time average real part of the wave number squared now depends on the pressure, the real part of the pressure that's acting on the bubbles, and also the full nonlinear changes of the void fraction. Also, the imaginary part of the wave number now depends on the transmitted pressure, the imaginary part of the pressure that is hitting the bubbles, and the nonlinear void fraction of the bubble. We use the modified Hoff model in our simulations to study the nonlinear attenuation, and we use our model, and this model solves for radius at time t, and the results of this will be fed into the model, and we will calculate the attenuation by finding the real and imaginary part of the wave number squared. The way that we modified the Hoff model, we accounted for the radiation damping by including the terms related to the sound speed, and also we have add the thermal dependence and the losses due to the thermal effects. If we compare the results of our model at very low pressures and for a void fraction of 5 multiplied by 10 to the power of minus 5 meter cube, we will see that at very low pressures like 1 kilopascal, the results of our models agrees very well with the linear model, both for the sound speed and for the attenuation. Here you see the normalized sound speed, which is the sound speed in the bubbly medium, divided by the sound speed in the liquid in the absence of the bubbles, and the results are in very good agreement with the linear model at very low pressures, and also the attenuation versus the normalized frequency are in very good agreement with the linear model. If we compare our model with the semi-linear model, we see that the imaginary part of the wave number squared, which is plotted here on the y-axis, versus the normalized frequency, agrees very well with the semi-linear model at different pressures. So we have, in red, we have 50 kilopascal. In the black line shows the 80 kilopascal sonication pressure, and the green line shows the 120 kilopascal sonication pressure. Here again, the void fraction is 5 multiplied by 10 to the power of minus 5 meter cube, and all these results are for a 2.5 micrometer radius bubble. However, the advantage of our model is shown in this graph here, where we plotted the normalized sound speed versus normalized frequency at different pressures. The semi-linear model and the linear model only predicts this blue curve for all the pressures for the sound speed. However, our model is able to show the evolution of the sound speed in a bubbly medium as we increase the pressure. We have recently experimentally validated the changes of the sound speed with pressure in the bubbly medium by sonicating monodispersed solutions of bubbles. If we want to classify the radial oscillations of the bubble in a wide range of frequency and pressure, we can classify the oscillations in these two graphs. The top graph shows a bifurcation of the normalized oscillations of the bubble versus pressure, and the bottom graph shows the attenuation of the bubbles versus pressure. And the oscillations of the bubble can be classified into sonications below resonance, sonication in resonance, which is shown in blue, as subharmonic resonance oscillations, which is below twice the resonance of the bubbles, and subharmonic resonance, which is twice the resonance of the bubbles when the bubbles are sonicated at twice the resonance, and period 3 and period 4 oscillations, which are sonications around 3 and 4 times the resonance of the bubbles. As we see, the maximum attenuation is when the bubble at very low pressures happens for when the bubbles are sonicated with linear resonance. However, as we increase the pressure, the attenuation of the medium decreases. When the bubbles are sonicated with frequencies below resonance, the attenuation of the medium is small compared to the resonance case. However, as we hit the pressure which is responsible for the pressure-dependent resonance oscillations, the attenuation of the medium increases significantly, and then it decreases. The interesting fact is here are shown here at very high frequencies, where higher order subharmonics happen, and as we see, the attenuation of the medium is much smaller compared to the resonance and pressure-dependent resonance cases. As an application for sonicating the bubble with pressure-dependent resonance case, we can refer to high-intensity focused ultrasound, where we can sonicate the we can have the focal pressure at this region where we have a higher pressure and higher attenuation, while we are able to decrease the attenuation prefocally at pressures where there is less than the focal pressure. We have compared the attenuation of our model, predictions of attenuation of our model at these pressures with monodispersed population of bubbles, and the peak of the bubble sizes were 2.25 micrometer, and the number of the bubbles are 5,000 bubbles per milliliter, and we see very good agreement. Also, we can see the drop in the attenuation by increasing the pressure, as we detected in our numerical simulations experimentally. So, in conclusion, we developed a new model to calculate the attenuation of a bubbly medium while accounting for the nonlinear oscillations of the bubbles. The results of the model were in excellent agreement with linear model at low pressures, and also very good agreement with the semi-linear model for the imaginary part of the wave number. We have a big advantage in our model where we are able to calculate the pressure dependence of the sound speed, and our results are initial results are consistent with experimental measurements of sound speed attenuation in monodispersed bubbles. Thank you.